Alright, I've moved the equation back up here. Now, let's expand this equation. So left-hand side, sum of moment. Okay? Moment could come from applied couple as well as forces. So, again, in this problem, there's no applied couple. Okay? So, the only moment are due to forces. First term, okay, let's take into account all these forces. So, FAX times moment arm R, and R in this case is 0 because FAX goes through point A, plus FAY times the moment arm, again also 0. Now, since they're both 0, it doesn't matter whether it's positive or negative. The third moment term is due to this weight right here, and this weight about point A tends to create a clockwise moment, so it's positive. So it's mg times moment on R, which is 1/2 of the length. Okay? So that's it. That's left hand side. Right hand side, you have this IA times alpha. Okay? Where alpha is the unknown. Okay? What is IA? Well, IA is the moment of inertia about point A. Now, point A is at the end of this slim rod right here. Now, is there an equation that's given to us? Well, let's check the textbook. At the back of the book, you see there are 8 common shapes available, including this last one, slender rod, which is just right here. Now, down here, you do see a few equations, okay? And you are given actually this I x prime, as well as y prime axis, and either axis are at the end of the rod, okay? Which means that this, for example, x-axis, okay, would be the case where this rod is rotating about this x-axis. The equation is given, okay? So, which is our case right here. This rod is rotating about the end point. And the equation is 1/3 ml squared. So this is the right in the book. I, okay, about point A right here is 1/3 ml squared, where L, okay, in this textbook refers to the length of the rod. In our case, the length is capital L squared. Okay? So, bring it back in here. So this equals IA is 1/3 ml squared alpha. Okay. Now what if this formula is not available? Okay? Because sometimes formulas are given for just the moment of inertia about the center of gravity. Okay? And this table right here, okay, which is the x and y axis through the middle, and the formula is given, okay, which is 1/12 ml squared. Now, some textbooks actually just give you this right here, okay, the centroidal axis. That's all. How do we get 1/3 ml squared, okay, for this moment of inertia about this end point? Parallel axis theorem. So let's digress a little bit, okay, real quick. Okay, to prove that this is actually 1/3 ml squared, okay, by using the mass moment of inertia about center of gravity, okay, and by applying parallel axis theorem. Okay, so digress a little bit real quick. All right, so we have a rod, we have center of gravity, we have this point A. So I about this point A, or about this axis, okay, going through point A in our board, equals from parallel axis theorem equals the I through center of gravity plus md squared, where d is the distance between G and A, which is this right here, which is L over 2. Ig from the textbook, or from a lot of textbooks, is 112 mL squared. Bring in our terminologies. So L is capital L squared plus md is L over 2 squared. Keep going. 112 mL squared plus this is 1/4 mL squared. Combine the two, that gives you 1/3 mL squared. Hey, check this out. That's all. Okay, so now we just keep going. This term disappears, this term disappears. So what's left? Okay, you're right. Okay, and then the mass drops out of the equation too. And then I have L, and then one of them drops out. Okay, so alpha equals 3 over 2 times G over L. Okay? So 3 over 2 times G, which is a constant, over L, another constant. So my acceleration of B equals L times alpha, which is L times, brings this in here, 3 over 2, G over L, cancel out. That's your answer. 1.5 times of gravitational acceleration. That's the acceleration at point B, right at this instant.